children, how are you? Oh my God, day 4. We got day 4, day 5, practice test, and a small test. It's going to be a small test this time. All this stuff can be found at www.nkinfinity.com. My name is Mr. Krause. You can call me Mr. Key. All right, so these are the notes for 10.4. Now, before I get started, got a very serious, I'm going to have fun in this video. I am going to have fun in this video, but I do have a very serious thing to say. And that's to all of you listening, and I hope you're all listening. This past weekend, the Hiltons Central School District lost a second student. Former student, I should say second former student. They both had graduated 2 or 3 years ago, or 4 years ago, maybe even up to 6 years ago. But we've lost our second student to this heroin epidemic that's going on. I can only ask you to please take care of yourself. Don't get into all of that bad stuff. It is a spiral downhill, and I don't care what anybody tells you. It is a spiral downhill, and if you need help, reach out and get the help. New York State looks like they're going to put a lot of money into helping people. So please, please, please take care of your friends. Don't be afraid to tell somebody that your friend is troubling or is in trouble. And this is for anything that's going on in your life. If something is bothering you, if you're being bullied, if someone's bugging you, if someone's getting bugged, if you're too afraid to say something and you want to just tell somebody, go tell somebody. Take care of your friends, okay? Take care of your friends. Take care of each other. Take care of anybody. That's what being a human and being a good person is all about, okay? So please, please, please take care of each other and take care. Oh, please, we got to get past all this. Hopefully we can get this all fixed. You know, the drug epidemic is going to get probably worse before better because everybody thinks it's okay to just start taking random drugs. It is not okay, all right? It is not okay. All right. After I have a public service announcement for my students and I need some coffee because I am not in a mood yet, I drink Dunkin' Donuts coffee. I'm always afraid I'm going to spill it on my white shirt, my new white shirt. So let's get started. This is an introduction to inference. And I've been talking about this and hinting about inferencing for a couple of days now. So we're going to introduce it to you. I'm going to formally introduce it to you today, and I'll finish it tomorrow. It's about inferencing. Now, what the heck does infer mean? Infer means, as defined by dictionary.com, I just happened to go there, to derive by reasoning, conclude or judge from premises, or evidence, whatever that says. As far as statistical inference, what we're going to do is draw conclusions based on or from data. I want you to make sure you understand it's not what you feel is not. It's not what you believe to be right. It's not what's in your heart that's right. It's what cold, hard facts say. You know, I'm one of those people that I hear something, you see it on Facebook. It's got to be true. You heard it on this news. It's got to be true. I am one that disbelieves almost everything I read because I'm not sure. How was the data collected? What were they using? Did they have bias? You know, and I want to draw my own conclusions. And so what's very important that you learn to do is take data from many different sources. And some of you, that means you've got to listen and read things that you may not agree with in order to figure out, wait, is there any validity to what they're talking about? And remember, everything in the world that's short term is going to be radically changed. It's like, you know, individual scores are radically different, but a group score is more stable. It's the same thing with any time we do change stuff. You know, in the short term, things are a little bit weird, but in the long term, we're going to find out, did anything change? Did anything not happen? You know, so anything, that's part of statistics, I guess. That was my political craziness, because we just went through a political craziness where everybody believes everything they read when 95% on both sides of it is garbage. All right, some of it's really good stuff. You got to weed yourself through all that. And you got to become a better discerner of learning. And I think this statistical unit will make you start to at least question whether or not the data is valid or not. Okay, so that's what we're going to be doing. When I come back, we're going to start this period, this day. All right. Let's see what we got. Let's try to explain it using this way. So Hilton's Principal. I always use Hilton. And for those of you that don't go to Hilton, I apologize. You have to suffer. If it bothers you, substitute in your own school. Penfield Central School District, Fairport Central School District, Brockport, Kendall, and all the others across New York State. I'm only telling you the ones in Monroe County. All right, so Hilton, a.k.a. your school's principal. And, this is one of my students this year, but, you could just institute your own name. John Hopkins Principal, Mr. Me, decided to have a random drawing of all seniors in order to determine which of the students will be allowed to go on the senior trip. Unfortunately, the school could only afford to send about 20% of the seniors, and the rest would not be allowed to go. His math department designed an algorithm to assign draw numbers by choosing birth dates in random order. Should assign numbers by choosing birth dates in random order. If the algorithm worked as originally intended, we should see a correlation coefficient near 0. So if it is truly random, we will not see a pattern. We'll just see dots all over the place because anybody in the thing could be picked. So if these were the days, months, and these were the days, and we just, 1 through 12 this way, and 1 through 31 this way, and we just randomly picked kids, we should have a nice thing here where our correlation coefficient should be close to 0, which really just means there is no relationship to the number that was picked and your birth date. Unfortunately, what happened... What discovered was that when they were all said and done, there was a correlation coefficient of negative 0.33. Now, negative 0.33 is not very big. It's not very big at all. A correlation coefficient of this magnitude indicates that students whose birthdays were later in the year tended to get lower draw numbers. And the lowest 20% of the draw numbers were chosen to go on trips. So basically what I'm saying to you is if your birthday happened in December, you had a better chance of getting picked to go on the trip. If your birthday was in January, you had a very poor chance of getting picked. So you have to answer this question. Is this very small or rather small correlation enough evidence to say Mr. Kessler's random drawing was fixed? I don't know why I put quotes here. Was it fixed? I don't know. Is it enough? You could get a correlation coefficient. I don't know. Maybe it is, maybe it isn't. We need to go, we could go on what we feel to be the correct answer, and this is what most people do. Most people will be like, when they're confronted with numbers that they don't truly understand or don't exactly understand, they just draw their own conclusions. Negative 0.33, that's tiny. That's nothing. 1 is perfect correlation, so that's not even half. So it's just random. If it's less than 0.5, it's got to be random. It's got to be random. Or they might say, well, it's negative, and that doesn't even make any sense. So yeah, it's fine. Who's to say? Are you able to say? I don't know if I'm able to say. So you can't just do that. That doesn't make any sense. So the math department took some time to look over their numbers and found that a correlation this far from 0 had a 0.002 chance of ever happening in a truly random drawing. In other words, it had a 0.2% chance of happening. So could I come up with this? What 0.2%? 0.2%. Or let me try to put it to you this way. In 1,000 drawings, this would happen twice. Wait, is that right? 2.2%. In 100 drawings, I don't know. If it's got a 2% chance of, so in 100 drawings, it would happen twice. Is that right? 0.2% in 100 drawings. In 100 drawings, 2% would happen twice. So in 100 drawings, 2% would, no. So it's 1,000 drawings. Now, I was right the first time. In 1,000 drawings, I don't know what I was thinking of. In 1,000 drawings, it would happen twice that you came up with such a correlation coefficient, or 0.002 probability of this ever happening in a random chance. So this led them to believe that the correlation this strong would almost never happen if it was truly random. Therefore, the lottery was unfair. It was fixed, and it was fixed to favor those whose birthdays were later in the year. Now, whether or not it was fixed by accident or it was fixed by some nefarious, demonic way of somebody had a friend, not demonic, but a nefarious thing happened and they wanted somebody in December to go, and they're like, oh, this gives them a higher probability. I don't know. But we need to actually make sense. So our goal is to try to figure out if we can come up with these numbers and say, yes, that's not ever going to happen, or no, that will happen, or whatever. We have to decide, and we have to make inferences based on data, not feelings. Okay, so here's what we're going to do. We're going to use two different kinds of confidence or statistical inferences. Confidence intervals. We will use confidence intervals to estimate the value of the population parameter. Significance tests will assess the evidence for a claim. Will assess the evidence for a claim. And this is a hypothesis test about, so you make a claim, we're going to see if it's true. So these are the two types of statistical inferences. Both types of inferences are based on sampling distributions. You can't do the whole population, so we need sampling distributions, which is why we spent the last couple of days working on sampling distributions before we can really get an idea of what is an inference. You have to understand how the sampling distributions are created, how they're made, how the standard deviation is created, how spread out the data is. The higher the n, the lower the standard deviation. All that stuff that we learned these last couple of days, we're going to use now to see if we can make some inferences. And therefore, they're going to report probabilities. To make inferences. And I'm going to tell you right now, because I don't know where this is going to come up later, I'm just going to tell you right now, generally we use the 5% rule. You'll see a 95% confidence interval. They'll almost always ask, especially on New York State Regents, is, are you 95% confident? Because if you're 95% confident about something that it will happen, then that's pretty confident. That's pretty confident. Now, in order to use a 95%, just don't forget, 95%, sorry about my poor thing here, a 95% chance of something happening means we have 2.5% down here and 2.5% down here. So when you're 95% confident that something is going to happen or could happen, it will happen in here, in between these plus or minus 2 standard deviations. And in this case, standard deviations of our sampling distribution. All right. So plus or minus 2 standard deviations, if we end up with a number that's out here, that's less than 2.5% on a tail, and in our last question, it was 0.002. Not this is, remember, this is 0.0025. So, excuse me, nope. This is 0.025. This is 0.025. This is 0.0025. So that, see how big out there, look how huge that is compared to just 2.5% in the tail. So generally, we're going to use a 5% rule as our general, no, that's not good enough, or that fails the test. And you'll see how we play with that in a few minutes. In order to make proper/accurate inferences, and we're going to talk about inferences, it is most important that the data be collected with a properly, I didn't leave you enough room here, randomized design in order to avoid bias, obviously. It is so important that you create a simple random sample with good design that ignores bias. We talked in the last couple of days about, I think it was yesterday, about the fact that, sometimes you have undercoverage bias, where I gave you the Hispanic example, where it looked like it was only 1.8% difference, but because of the way we created the data, that should never, ever, ever have happened. Therefore, it had undercover bias. You have to create and design a sampling or a survey that minimizes to the very core, the amount of bias, so that when we create these tests to see how good our data is, that they don't fail, that we don't put out bad data. We don't put out bad inferences. We don't say, yeah, we're pretty confident that that's going to happen, okay? Good statisticians spend a lot of time creating designs or designing designing surveys to avoid at all cost bias, okay? So let's go through an example. Do I have time? Hold on. I think I'm going to start. I'll be right back. So we did an ACT question yesterday. Let's do an SAT question. SAT is probably the most popular nationally standardized test. It is absolutely normally distributed. Guaranteed. That's exactly what they do. They have so many 800s, so many 700s, so many 600s. The bulk of them are going to be in the 500s, some 400s. The average will be somewhere around 500. It's how the test is created. They make it come out normally distributed. So the actual mean score of this previous year's test is not known, but the research giants of Verweer and North research firm randomly surveyed 680 high school students from across the U.S. and found out that the mean on the math section was 505 points. Should probably have a little space there. These 609 students were taken from a simple random sample from a population of all students who took the test. So again, that 10% rule, it applies. Again, nobody's going to care about that 10% rule in Algebra 2, but next year when you take stats, your teacher's going to address it with you. On a basis of this sample, what can we say about the mean mu in this population of all 1.7 million students who took the exam? What are we missing? What don't we know? And I told you we were going to get to a place where we didn't know this. What don't we know? And in this case, we don't know the population mean. Mu. We don't know mu. We don't have a clue. I never gave you mu. I have my X bar. My X bar is 505. My standard deviation, do we have a standard deviation? No, I have an N value equal to 680. That's all I got. I don't even have a standard. I don't have a standard deviation or a mu, do I? Hello. Now our sample mean, because it was taken from a simple random sample that can be used as an estimate. So our sample mean, because it was taken from a simple random sample, can be used as an estimator of the mean population mu. Since we collected the data appropriately, our sample X bar of 500 pi can be assumed to be close to the true mean of the population. Okay? So what does close mean? Furthermore, how would the sample mean X bar vary if we conducted this survey 10 or 20 or even 100 times? So instead of doing one sample of 680, I did 100 samples of 680. Or, that's a lot. That's a lot. So what would happen? What would happen if I did that? Well, I don't know. We'll talk about that as we go through. Let's talk about sampling distribution facts from previous chapters. Let's take a look at these. X bar is approximately normally distributed. X bar is approximately normally distributed. And we get this from the central limit theorem. central limit theorem, which says if we take a value n large enough, no matter what the population is, it will be normally distributed. Now, in our case, our original population was already normally distributed, so I certainly didn't need an n size of 680. I could have done it with a much smaller number, but 680 is more fun. So 680 is significantly large enough to make sure that our sampling distribution is normal. So just recall from our previous chapters that the original distribution, which many times I don't know, but for an SAT it's going to be normally distributed, which is unknown. I'm saying this poorly. The original distribution, which we don't know, doesn't really matter. So long as our n value is large enough. And 680 is plenty large enough. What else do we know? The mean of this normal distribution, normal distribution, can be assumed to be I don't know if that's proper English, assumed to be the same as the unknown population mean. In other words, we're going to assume, because of the central limit theorem and it's normal distributed, that our x bar can be assumed to be the same as our population mean mu. And finally, the standard deviation in a simple random sample is the population standard deviation divided by the square root of n. In our case, 680 students, our standard deviation would be sigma over the square root of 680. All right, so from long history of previous exams on a college board knows that the standard deviation scores for the entire population is sigma equals 120. So if we use this, sorry, I took a little drink of my coffee. So if we use this information, the standard deviation, trying to write neater, let me see this. Standard deviation of x bar would be (120) divided by the square root of 680. I'm going to check my math here. 120 divided by the square root of 680. Hate it. So 4.602. 4.602. We now have gone from a standard deviation of 120 to a standard deviation of 4.602. Woo! Of course, just like we would never know the population mean, we could never actually know the population standard deviation. This fact you're going to deal with in AP statistics. That's outside the realm. You'll be given enough information that you're not going to have to worry about that. You're going to have to know this formula, the square root of its old standard deviation over the square root of n, but we're not going to worry about not knowing the standard deviation. But in this case, we're not going to know the mean. So let's try to see if we can figure out what this looks like. So if we were to conduct multiple samples of size 680 students taking the SAT scores, they would have a sample mean x bar and would vary according to the normal distribution. So this is really mu of x bar. And so we're going to assume they're equal to each other. And we would have a standard deviation of 4.602. So from here to here, that one standard deviation would be 4.602. And remember, this is my sampling distribution. And I know it's approximately normal because my n value is large enough. So this is my sampling distribution of x bar. So I know that within one standard deviation, 4.602 that way, and actually 4.602 this way. So if my x bar was 505, this would go from what, 500 and almost 10 down to 500. So between 500, close to 500 and 510, I would find 68% of the scores. Now remember, that's from the empirical rule, the 68.2%. Oh, here we go. Forgot about that. So recall, it's coming up right here. Recall the empirical rule, let's revisit it, that approximately, let me get this out in black. Let's do it in blue. 68.2% of data will be within one standard deviation of approximately 95. It's actually 95.4. 95% of data will be in two standard deviations, and 99.7% of data will be within three standard deviations. So what am I saying about this? And we like to use that. Remember I told you we like to use that 5% rule. That 5% rule. So that comes from this 95% here. So that would be from here to here. Now remember, this is my mu of x bar. And we do not know this. This is unknown. We're assuming it to be the same as our x bar, but it's unknown. Again, this is my sampling distribution of x bar. So if I go out two standard deviations, go out plus two standard deviations, or in this case, what was that, 4.602, so that would be 9 if I go out 9.2 this way, and I go out 9.2 or minus 2 standard deviations, so this would be minus 9.2. In here would be 90. Ooh, that's terrible. Let me try this way. Let me color it with this one. So this area under this curve right here, this area would represent 95% of the probability. So it would be a probability of 95%. I should say 0.95. So is equal to, but the probability, it would be 95% chance that the mean score, the x bar score of 505 that we came up with, we have a 95% chance of being within two standard deviation of the actual mean. So that mean that we came up with, we are 95% confident that we are within two standard deviations of the unknown mean. We don't know what the mean is, but of that unknown mean, we're within two standard deviations of it. Now that's hard to wrap your head around what I'm talking about. Some of you, your head's a little swimming. So let's keep talking about that. I got some information here. I want to put it down for you. So Let's see if I can figure out how to make this more palatable for you. I'm going to try to, so based on the rule, let me pause and I'll be right back. More coffee. All right, every time I take a break, I drink some coffee. So based on, I'm going to have to do this neat. Based on the rule, 95% of all samples of X bar. So you have to remember, each X bar will be different. So if I conduct this survey of 680 students and you conduct this survey of 680 students, we'll be different every time we do this. We'll be within two standard deviations. In this case, it's 9.2, approximately 9.2. Away from the true population mean, mu. And I should have said of size n equals 680. So you have to, of size n equals 680. In this case, we will be 95% of them will be within 9.2 points away from the true mean. Remember, we're always trying to get the truth. What is the truth? Since we really don't know and never could know the truth, we're trying to get that. Let's try to say this another way. Whenever, let me do it a different color. Whenever X bar is within 9.2 points, within 9.2 points of the population mean mu, then we know that our mu is 9.2 points away from our observed X bar. And that this would happen 95% of the samples. So if I'm 9.2 away from points from the mean, then the mean is 9.2 points away from me, and that's going to happen 95% of all samples of size n equals 6, of n equals, of size n, size n equals 680. All right. Let's try to say it in the most simplest way we can possibly say it. In 95% of all samples of size n equals 680, the unknown mean mu, the unknown mean population mean mu is in the range x bar minus 9.2 to x bar plus 9.2. And in this case, it was 505 minus 9.2 and 505 plus 9.2. All right, so all of this is gearing us towards what's called a confidence interval. So we can finally say, this is what I'm going to say really neat, finally. We can say that we are 95% confident. Oh, we could say, let me say this better. We could say, sorry about that, we can say with, I like the way I wrote it here, 95% confidence that the unknown population mean, mu, on the SAT math for all students would fall between 505 minus 9.2 to 505 plus 9.2, or 495.8 to 514.2. So based on this sample, we're 95% confident that the unknown population mean mu, that we don't know what it is, would fall somewhere between 495.8 and 514.2. Okay, so I know it's not 100% yet, so I'm going to try to give you another way to visualize it in a second, okay? So what does being confident actually mean? What are we confident of? Okay, so we can draw two conclusions that we're confident of. Number one, the interval between 495.8 to 514.2 does in fact contain the actual unknown mean mu, the actual unknown mean population mean mu. That, okay, if we decide we're confident, then we're 95% confident that this mean does in fact contain the actual unknown population mean mu. Or our simple random sample was one of the very few samples for which X bar is not within 9.2 points of the true population mean mu. So let me write this out. Because we were 95% confident that our X bar was within 9.2 points of the mean. Number 2, this one, would only happen %5 of the time. Think about it this way. If 100 people did this, you had 100 students that are in stats classes all across New York State, and they surveyed 680 kids. And those 680 samples, those 100 samples of 680 surveys would yield results that 95 out of the 100 would be between 95.8 and 514.2. 95 of those kids would come back and say, oh yeah, my mean's in between there. Oh yeah, my mean's in between there. Oh yeah, my mean's in between there. And 5 of them would come back that said, oh, no, my mean wasn't in there. My mean was outside of that, which is not going to happen very often. So it would lead me to believe that those 5 probably did not do a good job sampling. Or it's just one of the weird 5 where it just happened by chance. By chance. Okay, remember, 5% is pretty low. Okay. Because we will never actually know if we are right, the population mean mu lies between 5 point. We can only say this. And this is kind of important in AP statistics, but it's not going to be overly important in this class. But we would say this, and this is what they require on APs. We got these numbers or results by a method that gives us correct results, that gives us correct results 95% of the time. So therefore, the interval from 495.8 to 514.2 is called a 95% confidence interval. Remember, we're using statistical techniques, and we're trying to eliminate or reduce our error. We're going to talk about margin of error, I think, tomorrow. I don't think that's today. Tomorrow. We're going to talk about margin of errors tomorrow. But we're using something where we want to shrink our margin of error. So we're using a method that is statistically correct and accurate 95% of the time. So therefore, the interval from 495.8 to 514.2 is a 95% confidence interval. We are 95% confident that we used a method that would result in this interval. Okay? Oh, I'm going to address a little bit with margin of error, I guess, right now, because I see it right here. So the X bar equal to 505 is our estimate. It's not 100%, it's our estimate. And our margin of error is 9.2 points. Since 505 is just an estimate, we are only sure, we are only 95% sure that mu lies within 9.2 points of 505 in order to catch the mean. All right, so let's take a look and see what this looks like graphically. All right, so here's what we did. Let's look at it in a diagram. I'm going to have to shrink this a little bit, I guess. Well, let me put this information off to the side here. What we came up with was we had 20 simple random samples. So of n equal to 680. And we had a 95% confidence interval. 95% confidence interval that the true mean would be within 9.2 points of our sample. So, let's see what this looks like. Now, what you're going to find is we have... Oh, I got to stop. I'll be right back. Okay, so what you're going to see below are 20 arrows. 20 arrows. Now, the dot represents the true... the dot represents our sample mean. So these dots represent what we would come up with for x bar. X bar. These are our x bars. And the arrows represent a standard deviation of 9.2. So notice there are 20 arrows. Maybe this kid came up with a standard deviation. Maybe his sampling standard deviation had a x bar of 500. But he's within 9.2 of what we came up with. Maybe this one had one of 507. Maybe this one had one of, I don't know, 503. I don't know what these are. But you'll see, and I'm going to highlight the one that's the problematic one. Only one of these, this one right here, this is 1 out of 20. All the rest of them, you'll notice that the arrows cross this line, the true mean. So the true mean is captured within this line. So this one right here, this one might have come up with an x bar equal to, I don't know, 516. Well, if I subtract that 9.2 to try to get close to where the actual mean is, I'm way far away. So I may have come up with, in this 1 out of 20 case, where somebody did a random sample and it did not give us the right mean. All the other ones captured the actual mean. The mean was kind of close to the x bar that we created. So this is kind of like this sample's net. Here's our mean, and we're going to pick up a net this big. And oh look, we captured the mean. And this one down here has a net. And the net's always the same size. It's just how far away this mean is. Oh, look, we captured the mean. Now, this one here, look at this one right here. Now, there's my net, and I barely captured the mean, but I did capture it. And I captured it 19 out of 20 times. All right, that's a visual. Hopefully over, when we play around, this will make more sense. So the Hilton Tribune conducted a survey of high school students in Monroe County. They created a sampling technique that would ensure that the data they collected would be random. The survey they conducted collected data from 1,200 students. All students were asked, should school start later than it currently does? Of the 1,200 students, 71% felt that the school should start later. The Tribune reported that there were 95% confidence that the margin of error was plus or minus 4.2% in their conclusion. What is the 95% confidence interval? All right, so what we have to do is we need to take 71 and subtract off 4.2. And we would get 66.8. Oops, 66.8. Or we'll take 71 and add 4.2, and we get 75.2. So our 95% confidence interval would be 66.8 to 75.2. We would be 95% confident that the true mean of what these kids actually felt would be somewhere in between those two numbers. So Miss Abori, being not the sharpest pencil in the pencil box, was announced to her friends that 71% of all students feel that school should start later in the day. Explain to her why we cannot state things so simply. All right. So I'm just going to read through this one, and you can write down whatever you need to write down. But we don't have enough information. It's unfortunate, but we just don't have enough information about the population to state what the exact population mean is. Remember, this is a sample of the population, but we used a method that would ensure that we are 95% confident that it's between 66.8 and 75.2. The 71%, that was just one sample. That was just one sample. Somebody else could do a sample and get 70. Somebody else could do a sample and get 68. Somebody else could do a sample and get 73. But those are all in the 95% confidence interval. So we are 95% confident it's between those two numbers, but we don't know exactly what it is, and nobody will ever know exactly what it is. So that's not possible. So explain to Miss Arbori what 95% confidence means. The method we used to collect this data, and I'm going to write this one out because I want you to write this one out. The method we used to collect this data ensures that the true value of the parameter or the population mean will be within 4.2 percentage of the sample mean X bar 95% of the time. That's what a 95% confidence interval means. We believe that we collected the data and we used a method that will ensure that the true value of the population mean will be within 4.2% of the sample mean 95% of the time. And it goes back to this. You know, that one arrow where it doesn't hit the actual population mean. All right, we're almost done. We got 2 questions left. So Miss Arbori, that statistical genius that she is, man, we just keep messing with her, right? Holy crap. Read that a 95% confidence interval for the SAT was from 495.8 to 514.2 on the math section. She was trying to impress the kids around her and stated that 95% of all students that take the SAT score will score between 495.8 and 514.8. Explain to her why she is not correct. Man, if 95% of the kids took between that. Okay, so again, I'm going to try to just word this one through you. She's not correct, first of all, that 95%. She's not correct because a 95% confidence interval doesn't tell us where 95% of the data is. It doesn't. What it does is a 95% confidence interval tells us that we are 95% confident, or in 95% of the sample means that the true population mean will be between 495.5 to 514.2. So it doesn't mean that 95% of the data is between these two values. What it means is the mean, the actual population mean, we have a 95% confident, we are 95% confident that the actual mean will be between those two. The data is going to be all spread out, all the way up to 800 and all the way down to 200. From 200 to 800. Lowest you can get is 200. The highest you can get is 800. That's going to be spread out all over the place. 68.2% will be within one standard deviation of the actual mean, and then 95, and then 99.7. But 95 is not going to be in that small little range. That's just never going to happen. All right. So New York State Parents Against State Testing collected a simple random sample of 1,800 students across New York State and found that the sample mean to be 705 with a standard deviation of 90. Found that the sample mean of I think this is of the math score. Is this of the math score? I think it's of the math score. The group knows that if they continued to take samples of size 1,800, they would get different means, but they wanted to know how close their sample mean is from the actual mean. So a sampling distribution X bar is approximately normal. What are the mean and standard deviation? Okay, so our mean is going to be X bar is equal to 705. And our standard, a sampling standard deviation is going to be 90 divided by the square root of 1,800. So let's see what that is. 90 divided by the square root of 1,800. All right. I hate when it does that. 2.90 divided by the square root of 2.1213. So 2.1213. So according to the empirical rule, about 95% of all the X bars will fall within two standard deviations of the mean. What is the 95% confidence interval for this data? So we need to take 705 and subtract off 2 times 2.1213. And we need to take 705 and add 2 times 2.1213. So this is the simple math. And the math is not that bad. It's the understanding of the math that's the difficult part of all this stuff. So we're going to take 705 and we're going to add 2 times this. And we're going to get that. And then we're going to take 705 and we're going to subtract 2 times this. So there's our confidence interval, some 70, and let's just round to the 10th place. How about that? 700.8. So our confidence interval is going to be between 700.8 and 709.2. So what in the heck? So we're going to write and I want you to write an accurate statement. I'm going to actually write this one out. We are 95% confident that the true value of the population mean mu will be in the interval from 700.8 to 709.2. So we used a method that will ensure that 95% of the time, the X-bar, or the sampling mean value, will be between 700.8 and 709.2, and we're 95% confident of that. Okay, that's confidence intervals. That's the introduction. Hopefully the homework isn't too bad. We got one more day of this stuff. We're going to be estimating with confidence, and we're going to be doing a little bit more work with it, and then that's it. We're done for the year. Yay! Oh my God, it's so exciting. Hit the subscribe button. Hit the like button. Tell me what you think. I know this stuff's a little bit heavy for you. We'll see how things go. Okay, kids, good luck. Keep working.